Okay, now we're going to tackle probably the most important topic in all of the course. That sounds a little hyperbolic, but I believe it to be true. This is the one thing that I would want you to leave the course knowing, because it's so pervasive in literature when you're studying research or you're looking at certain tests, particularly with medicine even. Even if you get a prescription and you open it up and you have this piece of paper that's really long, all kind of condensed down into the box, if you ever open that up and look at it, they will have all the p-values from all the studies that they did to see whether this drug is actually effective or not. And you can really start to understand research and how strong the research is if you understand this concept that we're about to study. So let's go back to our story of our free throw shooter. You might remember that our free throw shooter claimed to be an 80% free throw shooter. And so let's say that we take him down. This time we give him 50 free throws to shoot. So he goes down to the gym and he shoots 50 of them and he makes 32 of them. So he's shooting 50, he makes 32. That gives him a 64% free throw percentage. He claimed to be 80. So if we were writing hypotheses, we would have said that the null hypothesis is that his true percent really is 80%. But of course, if you doubt him, and we would have doubted him, I think, before he actually shot the free throws. And that's kind of important. You want to make sure that you write your counterclaim before you look at the data. But we were suspicious that he was going to be less than 80%. Now, I suppose we could have made this not equal to, but normally when somebody makes a claim like this and it's so high, relatively high, the doubt that we might have is that it's, well, not really as big as 80 and less than 80. In fact, if he shot 82 or 85 or 90 even, we would say, all right, yeah, he's probably 80. So that just seems to be right. Plus, usually in the problem somewhere, it will give you enough evidence to know which direction to go with your sign and the alternative hypothesis. All right, so 64% is what we got in our sample. He is claiming 80%. The big question we want to answer is this significant evidence or convincing evidence? Obviously, 64% clearly is less than 80%. That's not debated. What we want to know is this convincing evidence? Or we might even say, is this statistically significant? Is it so rare to be at 64 that we would doubt his claim? Or is 64% really not that far away from 80%? So for that, again, we could turn to some sort of a simulation. In your textbook, they actually have conducted a simulation. And we have a dot plot here that shows the simulation. And what did they do? It looks like 400. So they set up a computer to do 400 simulated 50-shot sets. So 400 times they simulated somebody shooting 50 shots. And it turns out when you do 400 simulations of that 50 shot, look at the percentages. Yeah, they're centered around 80% because that's the way the computer was set up. The computer is set up to do what the hypothesized value is, which is 80%. So if you are an 80% free throw shooter, this is typically what happens. Sometimes you're doing better than your average. Sometimes you're doing worse than your average. The key, though, is look where the sample proportion ended up. 64% is way on the bottom end. In fact, only three times out of 400 would a shooter, kind of just by random chance, be this bad if they were really an 80% free throw shooter. And 3 out of 400, you'll notice down here it was calculated, 3 out of 400 is less than 1%. So think about what that means. And because this is really important. The idea that we are representing here is maybe the most important idea in all of the course. If the null hypothesis is true, remember what the null hypothesis was. The null hypothesis was that his true free throw percentage is 80%. If the null is true, then there's only a 3 out of 400 chance that he would have been this bad or worse. And so because that's such a small chance, such an unlikely event, I hope in your mind you know what we should be doing with this claim. He claims 80. There's less than a 1% chance that he would be as bad as he was or even worse. So our conclusion should be that we should reject the null hypothesis. When this value, this probability value, is so low that it's rare, that it's not really likely, anything that has a less than 1% chance of happening, most people, I believe, would believe that that's not likely and that's rare and that's significant. So when P is low, we reject HO. So let me just finish that statement. Reject HO when the p-value is low. So this probability that we got right here has a name. I just kind of revealed it to you. This probability value, the probability of getting something that you got or even more extreme, if the null was true, is called a p-value. And p actually does stand for probability. So when the probability value is low, that means we are surprised, it's unusual, it's not likely, and so we tend to reject the claim or the null hypothesis when that happens. So when the p-value is low, we reject HO. So let's see if we can put that all together. I guess let's do one more example just before we get to that. So I've got, I think I do, let's see if I've still got this here. So let's look at one more example, which is very, very similar. This is the simulation of the CEO problem. And on the CEO problem, you might remember that we had a claim, a null hypothesis, that the true percent of CEOs born in June and July should be about 2/12, which was 0.16 repeating. However, we were suspicious that maybe that wasn't happening. They seemed to be underrepresented, so we were testing against less than 0.16 repeating. So if we did a simulation, kind of like we did with the basketball player, notice the null hypothesis, which is this right here. The null hypothesis is that it's really 0.16 repeating. So we set up a simulation to suggest that it's really 0.16 repeating, and if that's the case, this is what would happen if you did lots and lots of samples of size 375. So another simulation of lots and lots and lots and lots and lots of samples of 375. And then graphing what the proportion born in June and July would be. Once again, notice where 12% is. 12%, remember, is what we really got. That was the p-hat. I believe it was 45 out of 375, if I remember right. In fact, actually, it's right here. So we actually got 45 out of 375. This is our p-hat. So once again, notice the probability of getting results this extreme or even more extreme. That is the p-value, if you can calculate the percentage. And the computer did it. The p-value, or the probability that we would get results this extreme or even more extreme if the null was true, is less than 1% chance. So it's almost exactly the same p-value and decision. Because the p-value is so rare, so low, so surprising, we would tend to believe that the null is not true. So because the p-value is, and I'm going to put low in quotes because low is kind of not defined very well, is it? Because the p-value is low, we reject HO. Which, of course, that's a very statistical sounding statement. What that means, of course, is we do not believe that the true proportion of CEOs born in June and July is 16.7%. We would conclude that it's actually less because our sample was so far to the left. So that would be the practical conclusion. You will write that as well. This is kind of the statistical answer, and then we would follow up with a practical answer, which is in context. So that's the idea of a p-value. So now let's see if we can take a look at our guide and write out what a p-value is. What is a p-value? We said it, I've said it a couple times here. How would we say what a p-value is? Well, of course, it's in your textbook, but let me do just kind of a first run. A p-value, the letter P does stand for probability. So it's the probability of getting results. That would be a statistic, of course, a sample statistic, of getting results as extreme or more extreme So the p-value is the probability of getting results as extreme or more extreme than our sample statistic. Assuming the null hypothesis is true. Because remember, the models that we were using were always assuming that the null is true, and we put that in the middle of the distribution, which looked very normal-like. So that's what a p-value is. Your textbook is going to have a slightly different version of that, I'm sure. But this is one of those statements that's really packed with things. It's a probability. So the word, if you're ever going to interpret, you want to make sure you use the word probability. So it's a probability. And it's a range. So this extreme or more extreme, and then it's under an assumption. It's really a conditional probability. Assuming HO is true, this is the probability of getting results that far or farther. So those are the essential pieces, and of course there's context that you would put. So let's practice that with the CEO example. We found the p-value was less than 1%. That's pretty small, so we would reject the null. But of course this statement is just asking us to interpret. There will be several different ways to write this correctly, so let me try to tackle one way. I'm going to start with the condition. So I'm going to say if the percent of CEOs born in June and July is really 2/12, which was 0.16 repeating, or 16.7%. If the percent of CEOs born in June, July is really 2/12, that's my condition. The probability of getting a p-hat that is less than 12% is 0.008. So I chose to write the condition first. So if the null is true, basically. If the null is true, the probability of getting the statistic that is less than 12% is less than 1%. That's the interpretation. That's not the decision. The decision would be something like, because the p-value is so low, I would reject HO and conclude that the percent of CEOs born in June, July is actually less than 16.7%. That would be the conclusion. So watch the directions carefully. Interpret means you're kind of writing the definition. Making a decision is a different statement. The decision is more like what we said earlier. Okay. So let's keep going down. I'm going to skip a few things. There's two possible conclusions for a significance test. We know one of them because we just did it. So if the p-value is small, we reject HO. So you can imagine that there's another decision that could happen. We haven't seen one yet. But if the p-value is large, in other words, there's a good chance we could have gotten this by chance, we fail to reject. HO. Now, you might be thinking, well, that doesn't sound like the right thing. It seems like you should say reject HO or accept HO. Well, if you would think about that a little deeply, you might realize that that's really not logical. It's not reasonable. Just because you don't have evidence to reject something doesn't mean that it's true necessarily. You can think of lots of good examples of that. Just because you didn't reject it doesn't mean that it's true. It just means you don't have evidence to reject it. So one great example, if you think about this, is in the court of law in the United States. The U.S. justice system, when we make a conclusion in a trial, let's say, a trial decision, think about what the two possible conclusions are. When the jury comes back and the judge says, do you have a decision? There's two things they might say. They might say there is enough evidence. There was significant evidence, significant enough to pronounce guilt. They might say, we, the jury, believe the defendant to be guilty. Of course, the burden of proof would be the, beyond reasonable doubt. So if there's beyond reasonable doubt, that's like saying there's a small p-value and we would reject the null hypothesis and claim guilty. But if there's not enough evidence to convict somebody, if there's not evidence beyond reasonable doubt, they don't come back and say innocent. They come back and simply say not guilty. And that makes a lot of sense. Just because there's not enough evidence to convict somebody, that does not automatically mean they are innocent. That just means they're not guilty. So the thinking that we do and the way that we state the conclusion is exactly like we do in a court of law in the United States. So the two things that you will say, you'll either reject the null hypothesis or you will not reject the null hypothesis. You never, ever, ever say anything that acts like you believe the null hypothesis is true. That would be like saying in a court, well, then I know the guy's innocent. Just because they couldn't convict him, he must be innocent. That's not reality. That's not common sense. All right, so then some common errors, and later on we'll find out there's actually a better word here. We really should say mistakes, because unlike other uses of that word, these really are bad things. So there are some common mistakes that students make in their conclusions sometimes. One thing that's been pervasive even recently is no context. Always, 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 when you're explaining or justifying or concluding, make sure you put context in the story, whether it's CEOs or basketball players or whatever. Secondly, you never, ever, ever want to write any sort of phrase that sounds like you are accepting the null hypothesis. Now, it's not just the word accept. You might say, so, there's evidence that it's really 20%. No, you can't even say that. Don't say any evidence that you believe that the null hypothesis is true, ever. You can just say that there's no evidence it's not true. And then another common mistake is no linkage and by linkage we mean why did you make your decision? You can't just make a decision and say, I'm going to reject the null hypothesis, or I'm not going to reject the null hypothesis. You must say why you made the decision. And the why is simply the p-value. Here's your y. Your y is either the p-value is small or the p-value is large. That's your y. So it's not hard to write that, but you just have to put that in there. You can't just make a decision without saying why you did. Now, I hope that when I was writing these words back here, when I said if the p-value is small and the p-value is large, I hope some of you were thinking in your mind, well, wait a minute, what's small? 5% might be small to somebody, 10% might be small, 2% might be small. Good question. That's why we have this thing called a significance level. That will tell you how low is low, how small is small. The significance level in statistics is the percent that is kind of the decision line. Or you might call it the threshold. It's the threshold for deciding about p-values. And the significance level is going to have the letter alpha. Many times, as you might imagine, the alpha level will be 0.05. That's a very common one. But if you want to be more sure that you really have something, then you would want alpha to be maybe 0.01. Or like in medical studies, sometimes they go to 0.005. They really, really, really want to be sure. Or if you want to see something really amazing, when they make discoveries in physics, the alpha level is something like 0.0000001, something really, really tiny, because they want to be absolutely sure that this could not be something by chance. And so their threshold is way, way smaller than most things that are done in statistics. So when we say the p-value is small, what we mean is the p-value is less than alpha. So the second question here, when are the results statistically significant? The answer to that is when the p-value is less than alpha. That's what statistically significant means. Anytime you get results that the p-value is less than your significance level, that's statistically significant. All right, so I just kind of hit the big things. You now will have some practice over some of those. You also can fill out the rest of your guide to fill in kind of the in-between things that connect all the parts together, and you can get some more practice. So for now, that's it.